Welcome to the deep dive. We take stacks of sources, articles, research, tech docs, and pull out the really fascinating bits just for you.
And today, we're tackling something huge, a massive historical and, well, technical journey. We're tracing the evolution of security over like 4,000 years.
Oh,
Yeah, it's not just about a piece of metal. It's the story of controlling access, from ancient wood and rope things right up to, the digital tools managing software today.
that's right. So our mission for you today is to follow this kind of security arms race. We'll trace the physical lock history, the precision engineering, and then connect that whole journey to the abstract world of cybersecurity threats we see now in 2025.
hmm
Okay, let's unpack this, starting way back, 4,000 years ago. Because the oldest keys, well, they definitely weren't always metal, were they?
No, not at all. We start with the Egyptian pin tumbler system. That goes back to about 2000 BCE. And if you look at the engineering, it was surprisingly clever for a wooden mechanism.
So the key was what, like a big wooden bar?
Basically, yeah.
Yeah.
A large wooden block or bar with specific grooves cut into it or bumps on it. You'd slide it into the wooden bolt on the door.
Okay.
And those bumps had to lift these internal wooden pins up to just the right height, get them all aligned,
Uh-huh.
and then the bolt could slide back. Door opens.
It's kind of amazing that the basic idea, using pins of different heights inside something to block access, that's still the core of like almost every regular house lock today.
It absolutely is. A
Yeah.
4,000-year-old security concept, still going strong.
Okay, so moving forward a bit. First, millennium BCE. We start seeing changes around the Mediterranean, like the Homeric lock in Greece, sometimes called the bolt rammer, right?
Right. And this is where metal really starts entering the picture properly.
Ah, metal keys.
Yes, but interestingly, metal didn't automatically mean better security right away.
Mhm.
The Homeric lock used this very distinctive, big, sickle-shaped metal key, bronze or iron, usually.
Sickle-shaped, huh?
Yeah, and its job was literally just to ram or push the bolt back into the open position. Pretty brute force, really.
So, if it wasn't maybe as secure as the Egyptian pin system, why did it catch on?
Well, it was simpler in some ways. Locking was easy. Just pull a rope or a cord from the outside, and bang, the bolt slides shut.
Okay, convenient.
But opening it needed that big, specific metal key. The sources say it offered, limited real security compared to what came later, but it worked, and it was easier to make back then.
And what came later was the Romans.
The Romans, they made huge leaps between roughly 900 and 870 BCE. This was the real shift to, commercial all-metal locks, bronze and iron taking over.
And they didn't just copy the Greeks, right? They added something new.
Exactly. They introduced the warded lock. So instead of just pins, they put fixed obstacles inside the lock mechanism, little projections, walls, called wards.
Rewards.
Okay, for a key to actually turn and slide the bolt, it needed very specific notches or cuts to physically get past all those wards inside. That design became a standard for, centuries.
And didn't keys become more than just functional for the Romans, like a status thing?
Oh, absolutely. The key started to symbolize things. Wealthy Romans had locked boxes for their valuables, obviously. And they'd often wear these small, sometimes really ornate metal keys as rings right on their fingers.
Oh, like jewelry.
Yeah, it wasn't just about security anymore. It was showing off your status, your wealth, showing you had important stuff locked away.
Okay, so fast forward quite a bit now, leaving antiquity, moving into the 18th, 19th centuries, the Industrial Revolution. This is where things get really interesting, isn't it?
Oh, yeah. This is where it turns into a proper arms race, driven by precision engineering, new machines.
It's locksmith versus lock-a-picker, but with much better tools on both sides.
Exactly. A real battle of wits and metallurgy.
So who are the key players here? I know Robert Barron comes up around 1778.
Right, Barron. He's generally credited with the first, let's call it modern lock, the double-acting tumbler lock. It upped the games significantly.
How so?
It needed two separate levers inside to be lifted to an exact height, both of them, at the same time. No more wiggle room. Precision mattered.
Okay, that's a step up, but it didn't stop there.
Not at all. Just a few decades later, 1818, Jeremiah Chubb patents the Chubb detector lock. Now this was clever.
The detector lock, what did it detect?
Tampering. It had this extra mechanism, a detector lever. If someone tried to pick the lock, maybe lifted a tumbler too high or used the wrong key, the detector would catch and it would intentionally jam the lock. Dead. Couldn't be opened, even with the right key afterwards.
So it tells the owner, hey, someone mess with this.
Exactly. It's not just a lock. It's like an early mechanical alert system. You then needed a special separate regulator key just to reset the jam detector before your normal key would work again.
That's brilliant. A huge deterrent.
Massive. But the real high-security titan of the era, Joseph Bramah. His lock, patented back in 1784, actually, it was just leagues ahead.
Brahma. Right. What made his so special?
It used 18 distinct wafers, or sliders, inside. And the number of possible key combinations was, well, astronomical for the time. 470 million.
470 million in the 1780s. That's insane.
It really is. And Brahma knew it. He put his challenge lock right in his shop window in Piccadilly, London, starting around 1790.
Okay.
And offered a 200-pound reward, a fortune back then, to anyone who could pick it.
And how long did that challenge stand?
67 years.
67. Wow. Who finally beat it?
An American locksmith, Alfred Charles Hobbs. He did it during the Great Exhibition of 1851 in London, a huge event.
So Hobbs walks up, picks it, collects the cash.
Well, not quite that simple. Success is maybe relative here. It took him 51 hours.
51 hours.
Spread over 16 days. Constant, focused effort. Just think about that level of concentration needed for a purely physical, mechanical attack. It really shows you the peak of that era's security.
Incredible. So that precision, that complexity,
Yeah.
it eventually leads towards something more familiar, right? The Yale lock.
Exactly. That whole era fed into the Yale legacy. Linus Yale Sr. developed his first modern pin tumbler system around 1848, but it was his son, Linus Yale Jr., who really refined it. In 1861, Yale Jr. basically perfected his father's design, creating the cylinder pin tumbler lock we all recognize now. That small, flat key with the jagged edge.
Standard key in your pocket?
Pretty much. It took that ancient Egyptian pin concept and combined it with industrial precision manufacturing.
Amazing. So that basic pin tumbler idea, you said Egyptian, but is that definitely where it started? I hear there's some debate.
Yeah, this is actually a really interesting historical point that our sources dig into. For decades, everyone just called it the Egyptian lock. Case closed.
Or maybe not.
Well, some evidence, like finds at Khorsabad Palace near Nineveh, suggests similar devices might have existed in Mesopotamia around the same time 4,000 years ago. Others stick purely to the Egyptian timeline, like around Ramses II.
So, conflicting evidence.
A bit. But the really critical analysis, the thing that changes the game, points towards the Hellenistic period, specifically for the effective metal tumbler locks.
Okay, what was the key innovation then?
Springs. The Greeks, specifically early Hellenistic engineers like Theodorus of Samos back in the 6th century BCE, they're credited with developing metal tumbler locks that used pins or prongs. But crucially, they added springs.
Ah, springs. Why are they so important?
Think about the Egyptian wooden pins. They relied on gravity. Springs provide consistent downward pressure. This is really clear in the smart Hellenistic Laconian lock. Laconian means from around ancient Sparta.
Smart Hellenistic lock. Sounds advanced.
For the time, it was. It used tumbler pins pushed down reliably by a flat, thin iron spring. That spring makes sure the pins reset properly every single time.
Okay, reliability.
And, critically, it allowed the key mechanism to be operated smoothly with just one hand. It's a huge practical improvement over fumbling with a big wooden bar.
Yeah, much better user experience, you could say.
Totally. So this early Hellenistic period, that's likely where spring technology really entered the lock world. It wasn't the Romans who invented that bit, as people used to think. That tech influenced the Romans, and ultimately, it's essential for the smooth action of the Yale cylinder lock thousands of years later.
So we've got mechanical precision peaking with Bramah, and then widespread convenience with Yale. But physical locks kind of hit a wall, right? You can only make the metal so strong, the tolerance is so tight.
Pretty much. The physical arms race reaches a practical limit based on materials and, frankly, what tools an attacker might have.
So let's jump forward again, 2 centuries. Now, the modern lock is increasingly electronic. The game isn't about physical picking so much anymore. It's about wireless signals, software.
Right. The focus shifts entirely. We move from trying to physically force a mechanism to trying to compromise a signal or a system. Smart locks obviously offer huge convenience.
Like remote access, temporary keys from your phone.
Exactly. But there's a security argument, too. They're generally much less vulnerable to old-school physical attacks, like lockpicking or bumping, compared to standard mechanical locks.
And we see this everywhere now. Mobile credentials are huge. I saw a source mentioning Arizona State University, something like 80,000 students using their phones as their only key for campus access.
Yeah, they'd apparently call the phone the most protected credential available now, because it usually has multiple factors of authentication itself.
Right. And for businesses like apartment buildings or offices.
Huge operational savings.
Mm.
Think about it. No more replacing physical keys when someone moves out. No more calling locksmiths for rekeying. You just revoke the digital credential instantly.
Mhm.
Big savings on time and money.
Okay, but it feels like we've just swapped one set of problems for another. We move security from the physical door to the digital world. What are the new risks, especially thinking about, 2025 and beyond?
Well, the threats are definitely different. Less visible maybe, but potentially much more scalable. You've got remote hacking for starters.
How does that work?
Exploiting bugs or vulnerabilities in the wireless protocol. The locks use Bluetooth, Wi-Fi, Z-Wave, whatever. Or finding flaws in firmware that hasn't been updated. The attacker doesn't even need to be physically near the lock anymore.
So the lockpicker's toolkit is now code, not metal picks. We've traded the risk of a bump key for the risk of a zero-day exploit.
That's a good way to put it. Then you have malware and ransomware. That could infect the lock's control system or the management platform.
Making the lock just stop working. Or worse.
Or worse, imagine ransomware locking you out of your own building or home until you pay up. And maybe the biggest shift is towards credential theft.
Stealing the digital key itself.
Exactly. Cybercriminals focus on getting login details, maybe through phishing emails or malware on a phone or computer. Because why pick one lock when you can steal the master digital key that opens thousands of doors? That's far more valuable.
Scary stuff. And you mentioned earlier this idea of a lock goes even deeper, right? Like into the fundamental workings of computers.
Oh, absolutely. The core concept of a lock controlling access to something shared is fundamental in computer science. It's what we call a synchronization primitive.
A synchronization primitive. Okay, break that down.
The most common one is called a mutex. It stands for mutual exclusion,
Mutual exclusion, meaning
it ensures only one thing, one process or thread in the software can access and change a specific piece of shared data or resource at any given moment. It prevents chaos and data corruption.
so it's like the digital version of putting a physical lock on a file cabinet so only one person can change the files inside at a time.
Precisely. If the Chubb lock physically excluded tampering, the mutex digitally ensures mutual exclusion to prevent data getting scrambled when multiple processes try to write to the same spot simultaneously.
Just like physical locks, I imagine getting the number of digital locks right is tricky.
Hugely tricky. It's called the granularity problem, a constant balancing act.
Yeah.
If you have too few locks, say, one giant lock, protecting a whole huge database, then every process wanting to access any part of it has to wait in line. That's high contention. Things slow down.
Right.
But if you use too many tiny locks, maybe a lock on every single record, the overhead of managing all those locks becomes massive. And worse, you dramatically increase the risk of deadlock.
Deadlock. That sounds bad, like system crashing bad.
It is. It's a critical failure mode caused entirely by the locking system itself. Imagine two programs, A and B. Program A locks resource 1 and needs resource 2 to continue.
Okay.
Meanwhile, program B has launched resource 2 and needs resource 1 to continue.
Oh, they're stuck.
Exactly. Neither can proceed because each is waiting for a lock held by the other. They wait forever. The system grinds to a halt. It's like two people meeting on a narrow path, each refusing to step aside. Internal gridlock.
Wow. And that complexity must explode when you try to build big, complex software systems.
It leads to what might be the hardest problem in this area, the lack of composability.
Composability.
Right.
Meaning putting things together.
Right. It's incredibly difficult to take small software components, each using locks correctly and working perfectly fine on its own, and combine them into a larger system that is also guaranteed to be correct and free from deadlocks.
Why is that so hard, if the small parts work?
Because you often need to understand the internal locking behavior of every single component you're combining. Think about transferring money between two bank accounts, account A and account B.
Okay.
Internally, account A's software might use its own lock, L1. Account B uses its own lock, L2. The money transfer function needs to lock both A and B to do the transfer safely.
Makes sense.
But what if one transfer tries to lock L1 first, then L2? And at the exact same moment, another process tries to lock L2 first, then L1.
Deadlock.
Deadlock. The money transfer fails. Maybe the money vanishes into thin air, logically speaking.
Hmm.
To prevent this, programmers have to enforce some kind of arbitrary global rule like always lock accounts in alphabetical order or always acquire L1 before L2. But that requires knowing the internal details of every module you use, which becomes almost impossible at the scale of modern software.
What a journey, seriously. From these huge, clunky wooden Egyptian keys through the incredible precision mechanics that took Hobbes 51 hours to beat, all the way to programmers battling these abstract digital deadlocks in the code that runs, well, everything now.
Yeah, the evolution really highlights this constant push and pull, doesn't it? Between making something secure and making it usable, convenient. But here's a final thought for you to chew on. Think about the sheer complexity involved back then. Brahma figuring out 470 million mechanical combinations. And then think about the complexity now engineers wrestling with composability, deadlocks, subtle timing issues, and software locks. Which era, you think, demanded more raw ingenuity from its engineers? And which type of failure, the PIC physical lock or the deadlock digital system, poses the bigger, even if more abstract risk today? That's something to mull over.